Yeah, so hey everybody. So I'm going to discuss high throughput data processing with GenStage. Not that. That. So the intent of this talk is to act as a primer for data processing, introduce all of you to GenStage, and leave you with a list of production-ready libraries that use GenStage under the hood. So I'm going to frame this talk as, imagine you have a need for a data pipeline that can pull in and process data at least every minute. How would you approach that? And what tool does Elixir have to build this pipeline from scratch? So since you have a soft real-time requirement, or I guess this morning we discovered soft real-time is like a time guarantee. So if you have a non-event need for a data processing pipeline, you might use micro-batching. So micro-batching is just processing batches of data in tiny batches. Pretty self-explanatory, nothing too crazy there. Typically, this happens in intervals of less than a minute. And the lower bound is actually about a second. It's harder to do micro-batching in anything less than second intervals. Apache Spark tried to do that with Spark streaming, and they ran up to some pretty heavy limits there. This is less complex to reason about than true stream processing. You can just, let's say you have issue with a batch, drop the batch, and reprocess it at your next most convenient time. So trade-offs for micro-batching, there's more delay than actual event-driven streaming. True event-driven streaming, you can get events up to a microsecond or something crazy like that. But with micro-batches, you go above a second. So you have to really know whether or not you want to process your data as quickly as humanly possible, or can you make little trade-offs with that. It does require more tuning. If you're doing micro-batching and your processing window for a batch exceeds the batch lifetime, then what winds up happening is you run into resource exhaustion. The processing system will build up until it can't do anything anymore. And the effort required to move from a micro-batching architecture to event-driven streaming is actually pretty heavy. So when you're doing architecture considerations for this, really sit down and understand your data processing needs. It'll bite you later. So after you've decided you want to do micro-batching, you might consider something like partitioning. So once you have your data, you might need to split it evenly across a bunch of different processes. You might need to process sections of your data differently. You might need to, I don't know, let's say a very contrived example, you have events, each event has a color, let's say red, orange, and blue, for example, and maybe you want to process the blue and orange events differently from the red events. You would use partitioning to change how you're going to wind up actually doing that processing. So I guess I should mention the definition. Partitioning is splitting data for processing into subsets based on some identifier or attribute. So partitioning use cases, you might do partitioning to split data concurrently. If you remember the example given this morning with the Elixir changes, the idea of being able to do partitioning and then replication across those partitions, very similar case here with GenStage. An example is, let's say you have data that has a date in it, 12 months to a year. Maybe you partition by that month, and then you split that data over those 12 months. The second reason you might want to do partitioning is to trigger different processing behavior. So an example for this might be a type key. Each type needs to be handled differently. Examples I used earlier were the colors. A more real-world example might be something like web pages. You can imagine somebody's small blog that you've crawled needs to be treated differently from Reddit or something of that nature. So partitioning for concurrency. It's important to choose a partition key that evenly distributes the data as much as possible. If you have unevenly partitioned data, you wind up with data skew. Data skew can mean that certain nodes that are doing the processing take much longer to accomplish what they're supposed to, or in the worst case, actually just crash and fall over. Obvious keys like dates that I mentioned might actually be skewed. You actually really have to sit down and dive into your data to make sure that's not true. An example I like to use for real-world examples of skew, ice cream. People buy ice cream in the summer months. If you try to partition that by month, you're going to find out that May, June, and July have a lot more ice cream bought than the rest of the year. And then finally, you want to minimize partition shifts at different processing stages. So let's say you're processing by date, like I was just talking about earlier. and you switch from processing by date to processing by color, and it turns out that your dates and colors don't line up super well. So as you're going through the processing, you then have to shift all that data from node A to node B. It takes a lot of time, a lot of resource usage, slows down your pipeline significantly. Cool. Partitioning for processing behavior. So this is useful for control flow, useful for processing different subsets of data. And this can be combined with concurrency partitioning that I mentioned earlier. So these are not like mutually exclusive. Both techniques can be used in combination. And then finally, backpressure. I want to mention backpressure because this can really shut down your data processing pipeline. What is it? It's when a worker cannot process work as fast as it received during some temporary spike in load. So if you have too much load, not enough processing, your existing processing will be overloaded. You might run out of RAM, you might run out of disk space, et cetera, et cetera. From that, you'll wind up crashing your system. You might have data loss. The bunch of bad things will happen from backpressure. It's a pretty chief concern, not just in data processing. Like backpressure happens in like APIs and things like that too. So it's like pretty common across domains. So like I said, effects on a system, work might be dropped, resource limits can be hit, timeouts might happen, might all result in data loss. So what are some solutions to backpressure? Producers can buffer work until the consumer is able to catch up, can drop work depending on whether or not you can reprocess it, or you can do dynamic adjustments for producing and consuming based on the latencies. So a bunch of different techniques you can use to solve for backpressure. And then finally, I want to mention error handling. So a couple ways, a couple different types of errors, a couple ways to handle those errors. Dynamic backoff, I just mentioned, is really useful for backpressure. So changing how often your data is requested based on the latencies, the processing latencies. Retry logic with acknowledgements. If you're processing a batch, typically what you can do is acknowledge to your data source that, hey, this batch finished processing. If it doesn't get that acknowledgement, it'll just retry the batch at some later point in time. So it's like a very valid solution to handling that. Buffers, like I mentioned, and then rate limiting, which we're all familiar with from APIs. You can rate limit the number of requests that are being processed at any given time. So that was a pretty quick primer into data processing. Each one of these topics could honestly get like multiple chapters written on them in books. But I needed to kind of like pick a few central topics to make you guys familiar with them, and because they're pretty easy to demonstrate in GenStage. So I'm actually going to move over to my IDE and kind of walk through some code examples and show you what some of these topologies might look like just in code. So first off, is that legible to everybody? Cool, awesome, thank you. So I'm going to start with a really basic one. Basic example here is a producer and consumer. You're probably familiar with that example from like, I don't know, Java or something like that. You have a producer which creates work and a consumer which will consume and then process that work. So this is how you set it up with the GenStage. You start the GenStage and then you will subscribe one GenStage to another. So in this case, the consumer is subscribed to the producer. And then what that looks like inside of code, inside of their code, is you implement the GenStage behavior. The GenStage has like start link, init, handle demand. Handle demand is for a producer. So when a consumer asks for demand from a producer, that handle demand function will be called. It'll generate the given events or data or whatever you're trying to do for the consumer. In this case, I have a super contrived enum to list, one to demand. So I'm just generating a bunch of numbers for the demand requested from this producer. And then on the consumer side, after it receives that demand from the producer, it does this handle events callback. So here you can see all I'm doing is mapping over the set of events and then inspecting that event. In this case, it's going to be a number 1 to whatever the demand is. I think in the example I have set up, I have a max demand of 100, so when it's going through its processing, the most you'll see is 100 events. What I'm going to do now is go to my terminal, blow up my terminal. Oh. Hard to type with a mic in your hand. Actually, yeah, that would be awesome. Thank you. Lifesaver right here. So that's the basic example. Thank you. I'm going to do that like 2 more times. You might want to stay really close. Yeah. So basic example, what you can see happening here. Ooh, I'm getting some echo from something. 1 second. There we go. What you can see here is a bunch of numbers flooding my screen. So if I hit Control-C and I stop the process, what you'll notice is that it's a number from 1 to 100, which is the same as the demand that I set for the producer and consumer to play with. So consumer is just consuming all 100 demanded events and printing them to the screen. Pretty simple. For a more complex example, what we want to see now is something like this. So because I've gotten a little more complex, I've actually included the topology here. So you have a partition producer, which is going to go ahead and say, hey, we have all this demand, and now I want you to partition it numerically. So just in this case, I have it divided into 3 even sets. You can see that. You'll see that in code, but you can also see that right in other code later, but you can also see it right here just in like the calling function. I have 3 partitions that my consumers wind up using. Then we have a regular consumer, which I'm just calling a consumer, which is exactly identical to the same consumer in the basic example that I just did. And then this broadcaster producer consumer. So this is a little unique. What it does is effectively buffer demand from the partition producer. And then it'll go ahead and say, hey, I have all these events, and my consumers can subscribe to them based on some attribute of the data that's being processed. So what that looks like in practice is down here. Oh my God. What you can see here is I have this selector that I'm passing to the subscription function, and I'm evaluating the event and saying, hey, I only want orange events, or hey, I only want blue events. And then that'll be all that B and C process respectively. B will process orange, C will process blue. What that looks like in implementation is something like this, where the producer is largely identical to the basic example. The only difference is now I'm creating events with a color. So I'm not going to go too deeply into this, but I switched out producing numbers for colors. The broadcaster producer consumer, however, has this dispatcher, which is the GenStage broadcast dispatcher. And that changes the behavior of how events are given to consumers that subscribe to it. So another thing you'll notice is, OK, this producer has this little producer atom that's being sent back. But now we're sending back a producer consumer for, well, surprise, surprise, a producer consumer. What that's saying is, hey, I am this behavior. So if you send producer, you're a producer. If you send producer consumer, you're a producer consumer. If you send a consumer, you're a consumer. Producer consumer does not implement demand. It implements handle events, which was a little surprising to me when I was first using GenStage, because technically it acts as a producer, but it's really processing things more like a consumer. In reality, in this handle events callback, you'd actually do like work here to transform the data that you're receiving. I just go ahead and print that it's producing something. Like you'd probably, I don't know, do whatever transformation you want. Again, the web page example I gave earlier, maybe this would be where like you extract links or something like that. But it's really up to whatever your data is. And then like I mentioned earlier, the consumers are just really general consumers. They're the same as previously. There's no change in implementation from the basic example. Amos, if I can get you back to hold the mic. Thank you very much. And we're about 2 minutes over, it looks like. Time was. We good on time? Okay. So I'm going to clear this. Oops. OK, so I'm going to stop this. The difference that you see now is that the work has been partitioned to the consumers based on their color like we expected. So consumer B only gets orange, consumer C is only getting blue, A is red. red actually isn't partitioned any particular way. It just is subscribed to the initial producer, so it's not receiving that data in any special way. Somewhere around here, you should be able to see, if I scroll back far enough, yeah. You can see demand received by the initial producer, the A consumer prints red, then the producer consumer starts getting its processing, and then its children receive their respective events, and they print blue and orange. Thank you. So finally, I have one last code example that I want to show, and this introduces a rate limiter into the mix. So let me go back into my examples. Cool. And you can see here that this is pretty much the same as this one, but this A consumer now has a rate limiter in front of it. So pretty self-explanatory. A rate limiter is going to say, hey, there's some demand that I want, in this case 10 events, and I want it on some interval, in this case every 5 seconds. Now, a rate limiter is basically fully custom. There's no just like nice little like rate limiter in the library. You have to effectively implement it yourself. I'm going to zoom out a little bit. By implementing a few of the callbacks that are documented in GenStage. So I'm not going to go too deeply into them here because there's a lot, but all of this code is actually up on GitHub, and I have a link to it at the end of my slides. But I do want to show, by running that code, thank you so much. This is the last one. I appreciate that, though. So what you're going to see here is orange and blue flood the screen. And then you're going to see every 5 seconds or so, red comes in, starts getting produced or consumed by A. So we can just sit here. Should be another 5 seconds. Yep, there you go. That's the regular events. Yep, then you can see red start getting processed. So on a 5-second interval now, thank you. On a 5-second interval, those events are being processed. So the point here was not to be like, oh, after showing you this, you can go and like write the most complex like data processing code in the world. There's a lot that you can build with this. It was to show that GenStage is a really powerful building block that allows you to build like really complex data processing topologies. The analogy I would use here is like Spark is a big data processing system. You could use GenStage to build up from the ground to something like Spark. And with that in mind, I'm going to show one more slide. You can see initially I had all the code here, but I decided going through this on slides was going to be super painful, so did not want to do that. So yeah, I want to leave with this last slide. Bunch of super helpful libraries in Elixir that actually build on top of GenStage. And also GenStage itself is a library. It's not part of the Elixir standard library. It was created by Jose. But it's one of those things where it's super useful. I've used it in production code. Flow is super nice. Flow is built on top of GenStage, but what it's meant for is basically high-level concurrency of any type of data that you want. And then Broadway is basically meant for consuming events from like the internet and processing those. And then finally, I have the examples from the slide up on GitHub as well. But all these links here will take you to the respective either GitHub page or documentation for these libraries. And then, yeah, that's it for me. I will quickly plug Kingly Crow on Twitter, or GitHub ENTButler01 and GitLab Ian Butler. But that's it. I'd love to get questions.
Do you have any questions for Ian?
Hey man, first of all, like, nice to see your talk. Like, in your example, I saw that like it was like freezing a little bit when it was consuming the events. Like, this is something that your producer is taking, like, is like saying, sending events in like batches by time, or is some kind of issue on the consuming?
Yeah, so what's happening there in the case of the last example, the freeze is mostly from the rate limiter, effectively buffering the demand and then only responding to its consumer when the interval's up. So in this case, it was every 5 seconds, it was going to go ahead and like let the consumer process data. The reason you might do that is if your consumer is struggling to keep up with what your producer is producing, you can introduce a rate limiter to artificially restrict that and make sure that your consumer is not like overburdened. In this particular example, it was like super contrived, but I don't have like a really good production use case to show for this right now. So that's the reason why it was freezing.
Anybody else? Any other questions? Meryl.
Hey, thank you for this. I have been meaning to look more into this because we use Broadway,
Yep.
but I've not played with GenStage directly. So my question is around that, like, since Broadway is built on top of this, is there a time when you would reach for GenStage directly instead of going through Broadway?
Yeah, so I was working on a project that was scraping web data, and I wound up doing something like 500 gigabytes of web data like daily. And Broadway got to a point where I wanted to, I think, link one of the forward steps to like a previous step in the Broadway pipeline, and it doesn't allow you to do that with its topologies. So once I got to that, I was like, hey, I might need to do something custom, and that's when I thought about dipping outside of Broadway. Broadway's pretty strict on that it's like forward pass only, and I actually had an issue on Broadway for that, and like Jose was like, no. So yeah.
We have time for one last question.
A very simple question on the last slide. I couldn't read what the things were. I understand one was Broadway, one was Flow, one was something else, but couldn't read the rest. Yeah.
So Flow and Broadway are the two libraries that are built on top of GenStage. The top one is GenStage itself. And then the last one is literally just the examples from the slides. Hopefully all these slides get made available to you guys, because like there's just like GitHub repos on these that you can click and go into. Yeah.
All right, thank you, Ian.